Hi everyone. In this video, we're going to take a look at how to develop a mixing model. We're going to look at data from the Lassen Volcanic Center. This is Dome A from the Chaos Crags. These data are from Melissa Scruggs in Scruggs and Paterka. So here I've plotted silica versus MgO. I'll click on the data. I've created a graph here that plots these data and these columns. We can connect these two blobs of data, the felsic compositions down here and the mafic compositions here, as if they belong to a single mixing trend. Do they really belong to a single mixing trend? Maybe not. When I look at the data here, this looks like I have a linear trend that's at a slightly steeper angle and a flatter trend over here. So they could be separate mixing trends. But we'll start out just to illustrate the idea of building a mixing model, a linear mixing model, by just considering two-component mixing for the entire spread of data. Now to do this, we're going to use this equation over here. So this is basically a mass balance equation that says that the concentration of any element I, or oxide in this case, we're going to look at silica and magnesium in two separate calculations, that the concentration of, let's say, silica in the mixture will be a function of how much mafic material, that's the mass fraction of the mafic material that's being mixed into the system, multiplied by the concentration of silica in that mafic end member, plus the mass fraction of the felsic component multiplied by the concentration in that felsic component. So we need a mafic end member and a felsic end member. And we can define those compositions by just looking at this chart here. We could take the most extreme compositions, so our highest silica and our lowest silica examples, samples if we wanted to, but I'm going to pick something slightly outside that range. So for a mafic end member, I'm going to pick something that's a little more higher in MgO and lower in silica than what we observed in that blob. So let's say something that is about 50, maybe 55 weight percent silica and 5.5% MgO. So we'll have 55 weight percent silica and 5 weight percent MgO. We'll see how well this works. And then for the silica content, for the silica and MgO content of the felsic end member, we could pick something down here, maybe 72 weight percent silica and let's see, maybe 0.7 weight percent MgO. We could plot these and see how well they look. So we'll just select those, select the chart and go to Edit Paste Special. We want a new series and put the X values in the first column. And if we have, well, that orange dot is not quite as far outside as what I really wanted. So I'll just adjust this so that its silica content's a little lower. And I want something where a single line will hit most of those data. So for 53% silica, I think I want something that's a little bit higher in MgO. So we'll pick 5.5. Yeah, that looks like it'll work. If we put a line through those dots, we should get something that'll capture a lot of that variation. So here's our mafic end member, 53% silica, 5.5 weight percent MgO, and our felsic end member with a little more silica and a little bit less MgO. To build the actual mixing model, though, what we're going to do is use this equation. We're going to make up some values for the X mafic content. We'll let X, the amount of mafic material, go from 0 to 1, and we'll do it in increments of 0.1. So as a shortcut to creating that, I'm going to enter 0 and then 0.1. And then I'll move the mouse until it makes a black X. And then I'll just hold down the mouse pad until I get to a value of 1.0, indicator on the right. So now I've got a value of X mafic that goes from 0 to 1. Now, there's only two components. So if anywhere where X mafic is equal to 0, the amount of felsic material, this fellow over here, would be equal to 1. And anywhere where the mafic is equal to 100%, then the felsic content would have to be 0. In short, with only two components, we can always get the felsic fraction by simply taking 1 minus whatever the mafic component is. We could do this because we just have two components. If we had a third or fourth component, it would not be so simple. All right, For the CI, the concentration of the mafic, that's this over here. So this is really the CI for the mafic fellow. And then for the CI felsic, we've entered it in this row over here. So for the equation for silica, to get the mixture, it would be equal to the amount of mafic multiplied by the concentration of silica in the mafic end member plus the amount of felsic, or 1 minus the mafic, multiplied by the amount of silica in the felsic end member. I want to be able to fill down, so I'm going to have to add some dollar signs. I don't want these rows to change, the red and the orange. So for the p-values, P8, I don't want the 8 to change, and for P7, I don't want that to change. So now I can fill down, and I have a mixing line that goes from 72% silica when I have 0% mafic end member, and 53% silica when I have 100% mafic end member. I'd also like to fill this to the right. I could re-enter the equation over here, but if I'm using these N and O rows for the mafic and felsic amounts, I can simply put a dollar sign in front of the O and a dollar sign in front of the N, and now I can hold those rows constant and then fill down here, and I'll get the silica and MgO contents for the mixtures. Let's copy this, and then we'll go to Edit, Paste Special to put these in. And there we have, these aren't data, this is a model, and so to distinguish the model, I want to change the formatting a bit. I want a solid line, and I want the markers to look like hasher marks. And we'll make those hasher marks a little bit bigger. So there we have a linear mixing model. It's not very good. It's missing a lot of the mafic end members here, but we can adjust that by, let's say, adjusting the MgO content down a bit. So if we make it 5.3, it does a little bit better, maybe 5.2. So we could fuss with the end members to try to get that line to fit as closely as possible. Before we end this series, though, I'm going to change these hasher marks so they're a little more clear. I want to be clear about what these hasher marks mean. These points along the line are telling us the amount of felsic and mafic material that are explaining these mixtures. So our interpretation is that all those gray circles, those individual samples that we've analyzed, are a mixture of a mafic fellow over here and a felsic composition over here. But of course, the importance of the model is it tells us how much of the mafic is in each of these samples. So let's zoom in. If I want to explain, let's say, this guy over here, it's very close to the mafic end member, but it's not 100%. That hasher line represents the 10% mark. That would be this guy over here, 10% felsic and 90% mafic. So we could insert some text. So we'll insert a text box that I'll just put over here, and I'll write xm equals 0.9. Stretch that out. So this hasher mark there represents the case that the mafic end member represents 90% of the mixture. This hasher mark here would be 80, and then 70, 60, 50, all the way down to 0 when you get over here. We could also label these hash marks relative to the felsic end member. So this fel that is 90% mafic could also be written equivalently as 10% felsic. So these hasher marks tell us how much of the mafic and felsic end members are needed to explain any one of these magmas that are nominally produced by magma mixing. Now, as we said at the outset, this looks like it has a slightly steeper trend than this trend over here. So we might have a very good mixing model. It looks like we've done a very good job of explaining these data down here. The data are linear and they're falling pretty close to the model that we've set up. But we might want a new mixing model that has a steeper trend over here, maybe a mafic component over here and a felsic member down here. We could play the same game. We can actually just revise the model that we've set up here. So we can have a model with, let's say, 6% MgO, and let's say something that plots over here, so about 60 weight percent silica and maybe about 3 weight percent MgO. Will that work? Well, maybe we need a little bit less MgO or a little bit different amount of silica. So you could see we could have kept that original model, and we probably should have saved it because we had a nice model to explain these data over here. But the beauty of setting up the model in this way is that we can make edits and copy this out and build new models to explain whatever subset of data we want. Anyway, that's how we do a linear model, in this case for magma mixing. But of course, you can use the mass balance equation to mix pretty much any kind of geochemical data you like.